So I went really fast, okay, through thermal and transport. Again, I just wanted to give you guys a flavor of what's going on there. So you know where these modelers are getting their data from or not getting their data from and how they're doing it. Now, again, the last important part is the kinetics, the rates. Okay, how are we going to, thermal transport fine for species. Now, species might be 100, 200, 1,000, but the reactions are always 10 times more than the species. So, if we could calculate from quantum chemistry for species, it's already been a challenge. Imagine now for kinetic data actually getting accurate values. So we need, again, good tools, good analogies, good approaches to predict, or to estimate kinetic parameters, and then to build models which try to predict very complicated phenomena like ignition, flame speeds. We'll talk about those tomorrow. So now what we're going to do is we're going to go through how we develop the reaction mechanism, and then identify the reactions, and then how do we assign rates for those reactions. And this is an example for hydrocarbons. So we know the different types of reactions. We have initiation reactions, propagation, branching, and termination, right? So if you have a hydrocarbon like butane, you can start very simply and say, okay, I have different types of initiation reactions. And again, we're just imagining what these could be. Of course, we write this is butane, so there's a carbon, a carbon, a carbon, a carbon, 4 carbons, and 10 hydrogens. Well, one potential initiation reaction is just the breaking of a CC bond, right? The CC bond in the middle leads to the formation of 2 ethyl groups, 2C, 2H5s. You could break the bond here. So you could have a methyl plus a propyl, so methyl plus 1 propyl radical. You could also lose a hydrogen. Yeah? So actually, these are the only 2 scission reactions that are possible. The scission in the middle and the scission on the side. Well, if you break on the other side, it's the same reaction. It's not any different. Yeah? You could lose an H radical. You could lose an H radical off the primary, the first site here. So you form H plus 1 C4H9. 1 C4H9 is a radical on the primary site. Or you can lose a radical from the second carbon, and then a hydrogen from the second carbon. So you get H plus 2 C4H9. So these are all the potential initiation reactions, unimolecular initiation reactions. If you have pyrolysis of butane. Pyrolysis of butane is without oxygen, right? Of course, if oxygen is there, you might have some bimolecular initiation reactions. But in the absence of oxygen, there's only 4 possible initiation reactions for butane. There's nothing else I can think of here. If we do the same abstraction on the other side, it's the same. They're the same reactions. They're not different because it's a symmetric molecule. Okay, then what happens? Well, then you have these radicals, and you got to figure out what happens to these radicals. Well, ethyl will have to undergo some reactions. We'll have to deal with those. Methyl and propyl will undergo reactions. So we can also see, though, now that we're making radicals, we should have some chain propagation reactions. So after initiation, we start to think, what are all the different propagation reactions? Well, the radical, for example, the fuel radical, 1C4H9, can react with the parent butane. Yeah? We say any radical can react with the parent hydrocarbon to abstract a radical. This is a hydrogen abstraction reaction, okay? And hydrogen abstraction, we take one radical together with the neutral, we remove a hydrogen, and then what do we get? We get a neutral species. If hydrogen radical is abstracting, it takes another hydrogen, it forms hydrogen, neutral. If methyl is abstracting, it forms methane, and then it makes another radical, a fuel, in this case, a fuel radical. So, and we have 2 different types of fuel radicals because you can only take hydrogen from one of 2 different sites in butane. And like this, you propagate your reaction system, okay? And you write out all these different propagations. And finally, termination. So termination is the recombination of 2 radicals to form a neutral. So what are the different radicals? Well, we had radicals like ethyl and methyl and H, and then radicals related to the fuel. Well, one potential termination reaction is methyl plus methyl goes to form ethane. And similarly, methyl plus ethyl goes to form propane. Well, now you form propane in your system, and ethane, and now you got to deal with the initiations of those and the propagations of those. And like this, you see quickly how your mechanism can get pretty big, yeah? And then again, this is only for pyrolysis. We haven't even added oxygen in yet. Simply the pyrolysis of butane in the absence of oxygen. The other reactions possible are what we call radical decomposition reactions. So this is where you have a fuel radical, and the fuel radical undergoes a decomposition to form another radical and a stable species, yeah? So we have a radical site here for butane, and it can break plus CH3. We should get propene plus CH3. That's this reaction here. If I have a radical on this site here in the middle, we have a reaction, a radical decomposition reaction. Radicals are unstable. They want to do one of two things. They want to recombine with something else, like another radical. They want to react with the parent fuel to abstract a hydrogen, again, to become neutral, or they want to decompose. And again, the favorability of each reaction depends on the temperature and the reacting environment. So if this one is to decompose, the most common reaction, we call it a beta scission reaction. Beta scission, okay? Beta scission reaction happens because this bond is this radical creates electronegativity. It's pulling electrons in that direction. It makes this is the alpha bond here, because it's alpha to the radical site. This is the beta bond, beta to the radical site. So it's pulling electrons, pulling electronegativity towards the radical site. It makes this beta CC bond very weak, or weaker, and then therefore it breaks. So anytime we see a radical, we typically say it undergoes a beta scission reaction. Does it mean alpha scission reactions are impossible? No. You can have alpha scission reaction, but they're highly unlikely because, again, this is the bond that's way weaker. So nobody puts alpha scission reactions in a kinetic model because we know that 99.9% of the time, the one that will break is the beta bond. If you want to break the alpha bond, you got to go to, the reaction can happen, but it has to be at a much higher temperature because this bond is very strong. So you need to be at like 2,500 Kelvin or 3,000 Kelvin for this bond to break. And in combustion, we never see that, yeah? So maybe if you're doing a fusion reaction, if you're doing a kinetic model for a fusion reactor, you might include alpha scission reactions and different things that happen at very high temperatures. But here, we don't worry about it. So like this, different beta scission reactions, if the radical's on the first site, again, the beta bond breaks, you form ethylene plus ethyl. You could also have beta scission of an H radical, yeah? So there's one other beta. This is a beta carbon-carbon, but there's a hydrogen here. This one is also beta. This is a beta carbon hydrogen. But beta carbon carbons are weaker than beta carbon hydrogen. But you can also include the hydrogen scission reaction. That's the one that's shown here, and so on. So you have 5 different scission reactions that are possible, or yeah, 5 different radical decomposition reactions that are possible. Again, you write all these out. Now you're forming olefins or alkenes, butene, propene. You need more reactions to deal with those. And if you build this model, then you can start to simulate stuff, yeah? And I'll show you, of course, how to build the model. But if you build this model, then you can look at the decomposition of butane, the formation of ethylene, ethane, the formation of methane, and so on. Then this is all dealing with the decomposition of the fuel. But eventually, if you pyrolyze butane, what happens? You'll get benzene and PAHs, and eventually you'll make soot. Well, all of that has nothing to do with the butane decomposition. It happens sometime later in the process. So what happens is things like ethylene, acetylene, they start reacting to form kind of like a chain growth reaction. As the chains grow, then you form cyclics, you form benzene, then the benzene grows, it forms PAHs. These are what are called pH kinetic models. And of course, many people in the community also work on pH kinetics. We won't go into detail about PAH kinetics and soot formation. That happens after the fuel decomposes. And again, the kinetics, the approach is the same. You try to understand what are the different types of reactions you can have for chain growth, and then you build your kinetic models according to that. But again, in the scope of this course, we'll deal with how we just do it for fuel decomposition reactions and standard combustion processes. And of course, once you have these models, you can do things like reaction path analysis. You can look at which pathways are more important or less important during the combustion process. Okay, another example, propane, easier than butane now. Yeah, propane, initiation reactions. You break the carbon-carbon bond, you make C2H5 plus methyl. You break the carbon-hydrogen bonds, you make H plus propyl radicals. Different propagation reactions, different termination reactions. So you saw, it's quite similar to that of butane. You always have the same types of family of reactions. This will be the same. You can go to an alcohol fuel like ethanol or butanol. You can go to a biodiesel, ester. You can go to an aldehyde. Same types of reactions, okay? Initiation, radical decompositions, abstraction reactions, recombination reactions. And you can do this with different fuels. And this is a comparison for the flame structure of N-heptane, NC7H16, and N-dodecane, C12H26. This is actually showing us that same burner stabilized flame. If a fuel is entered into a burner stabilized flame, how do we, sorry, this is not a burner, this is a counterflow flame. So it looked like this one. So a counterflow flame, where you have the flame in the middle. If you put N-heptane and N-dodecane, you start to see they lead to the similar types of intermediates, ethylene, carbon monoxide, carbon dioxide, at relatively similar rates. And the next slide is showing laminar flame speeds. These were measured at University of Southern California at different equivalence ratios on this axis, different carbon atom for the alkanes. This is a laminar burning velocity. So it shows here N-heptane is C7, is the frontmost curve. N-hexane is the green, N-pentane C5 is the yellow or orange, and in the red is N-butane. All these fuels, they have different carbon atom length, but they have the exact same laminar flame speed. That's what these curves show. So at maximum, they're all around 55 centimeters per second at this temperature, I think of 353 Kelvin and 1 atmospheres. Similarly, they've done it for C10, C11, C12, C13. All of these, again, have pretty much the same laminar flame speed. So why do all these alkanes, which are different chain lengths, different structure, but when you burn them, they give the exact same laminar flame speed? Well, we'll try to understand that. We'll try to see from the model. The model should explain this, yeah? Of course, the fuels are different, their structures are different, but in the end, something is happening in the process that makes them eventually all the same, yeah? And we'll explain this by the end, why all these flame speeds are the same. Well, it comes down to because the types of reactions that are happening, yeah, are similar. So if I want to build a model to predict flame speed is a high temperature combustion phenomenon. The reactions are happening in a flame. The flame's temperature is around 2000 Kelvin. It's preheating the mixture before the flame to about 1000 Kelvin, and all the reactions start happening. So if you're trying to simulate flame speed, all you need are 9 different classes of reactions, and these are the 9 classes. So the first class is unimolecular fuel decomposition. The second class is hydrogen abstraction from the fuel. Third class is the decomposition of the fuel radicals. The isomerization of the fuel radicals is the fourth class. The fifth class is the abstraction from the alkenes, which are the intermediates that are formed. Addition radical reactions for alkenes, alkenyl radical decomposition, alkene decomposition, and retroene. So 9 classes, and I'd say the most important ones are the first 5. The last 4 are actually less important. And I know that from experience, but again, anybody wants to build a new model for a new fuel to predict flame speed, which was never done before. You just go and build your model for these 9 reaction classes. And you write down all the reactions that are possible, and then you know all the species, and then you get the thermal data for those species and the transport data for those species. And of course, you apply kinetic rate constants for all the reactions. And of course, that's what we're going to do. We're going to see how to get all those rate constants. So first, write the reactions, then you write the rate constants for those reactions. Now, this is 9 reaction classes, and this actually does not only apply to alkanes. You can apply these 9 reaction classes to any fuel, any hydrocarbon fuel, even ammonia will do the same. Of course, there won't be alkyl radicals. You'll have ammonia radical, NH2, but we'll do the same thing. If we have new types of hydrazine, ammonia-related fuels being formed, we'll use the same classes of reactions. So we can do this for paraffins, again, those alkanes. We could do it for naphthenes, which are cycloalkanes. We could do it for aromatic fuels, same 9 reaction classes, olefins. So all of these, the same reactions will exist. Of course, the rates will have to be different because depending on the structure of the molecule, the type of the reaction might be the same, but the rate of the reaction will be very different. So that's what's going to distinguish one molecular structure or one fuel from the other. Is not the types of reactions, it's going to be the rates of the reactions. Okay, so let's start building a model. This is our model, okay? This is our molecule for our test. It's a molecule, it's called 4-methylheptane. Yeah, 4-methylheptane is an isomer of octane with a methyl branch in the middle. Okay, I just chose it for example. It could be any molecule you could pick. And we're going to see, actually there's no paper today on the combustion kinetics of 4-methylheptane, okay? So if somebody wants to write it by the end of this class, yeah, you can write it. And of course, you need data to validate. There's no data either to validate for 4-methylheptane. But 4-methylheptane does exist in gasoline fuel. It's an isomer of octane. I've built models for 2-methylheptane and 3-methylheptane, but never for 4-methyl. You can see here, what does it look like? So the first thing you see, I got a new fuel, a new molecule, I want to build a model for it. We'll try to understand what are the different carbon atoms that are there, how might the reactions proceed. Well, this 4-methylheptane has 3 different primary carbons and 4 different secondary carbons, or 4 secondary carbons. 2 of them are actually the same as the other, and 1 tertiary carbon. And the first thing we always do, anytime we look at a new molecule, we say, what is the bond dissociation energy of the different bonds? That'll give us an understanding of like where are the weak points, where are the strong points, where's the reactivity going to be mainly driven by, yeah? And we see here, okay, primaries have a bond dissociation energy for the CH of 103 kcal per mole. Secondaries are 98 kcal per mole. Tertiaries are 94 kcal per mole. These are the CH bond dissociation energies, yeah? And that's going to tell us that the weakest hydrogens to remove is going to be the one with the lowest bond dissociation energy. So the hydrogen coming off this carbon in the middle is the weakest of all of them. And we said we have hydrogen abstraction reactions. So hydrogen will be preferentially abstracted from here. And in the primaries, the bonds are the strongest, so they're going to be the least likely to abstract. Okay, we skip the next one. You already know what bond dissociation energy is because we talked about it in thermo. This is a table of showing different bond dissociation energies. CH3H, so that's the primary, the secondary, the tertiary, the quaternary, what's this one? See, this is a branch, another branched one. And then you have, this is finally a quaternary connect. So 97 is, was tertiary. Oh, sorry, these two are the same. This is a secondary and a secondary, just one is in ethane, the other is in propane. And these 2 are tertiaries, one is in isopropyl and isobutyl. So they're just, you see they're roughly the same. And then, again, these are the carbon-carbon bond dissociation energies. So 2 methyl groups, the carbon-carbon bond dissociation energy is 88, then 85, also a carbon-carbon. If there's a branch, a secondary, you have 84, and then a tertiary, you have 80. So this also tells you why in a molecule you break the carbon-carbon bonds before the carbon-hydrogen, because they're always weaker. Carbon-hydrogen are anywhere from 97 to 105 kCals per mole. Carbon-carbon bonds are like between 80 and 90. But abstraction, of course, abstraction is always of a hydrogen atom. Scission is typically for a carbon-carbon atom. And then you can find these kinds of tables for many different bonds. Carbon-hydrogen, carbon-fluorine, carbon-carbon double bonds, and so on. And this is a useful book, a resource. It's basically a book with all different types of bond dissociation energies. So this is one table of that book. So bond dissociation energies for many different types of bonds. And again, if you're interested, like we now build molecules for ammonia. The first thing I do for ammonia, plot the bond dissociation energies for ammonia. Of course, there's only one NH bond. But then if you have that with mixing with hydrogen, sometimes you mix ammonia with heptane, and then you want to see which fuel is going to react first. You can make a lot of understanding just from the BDEs. We do a lot of work on sulfur-related fuels. Again, for sulfur-related fuels, you just look up and find out what the different bond dissociation energies are. That's the first way to start to understand, okay, how am I going to build my reaction model and where the important reaction is going to be. Okay, this figure just has more bond dissociation energies if you're interested. So for aromatics, for aldehydes and ketones, for alcohols, all of these things have been tabulated. And I'll show you how we will use the bond dissociation energy to also estimate the kinetic parameters. Okay, and then here, paraffins, we said, CC bonds between primary and secondaries, 84, between two secondaries, 82. Isoparaffins, the bonds become weaker because of the tertiary group that's there. So that 4-methylheptane, some of those CC bonds are going to be weaker because they're next to a tertiary group. So let's start building the model now. We're going to look at only 6 reaction classes. We're not going to look at reaction classes 6, 8, and 9. They're not very important. We're going to start from the beginning, okay? And look at the different reaction classes and how do we assign the rates for these different reactions. So the first one, okay? The first one we said is unimolecular fuel decomposition. This is the initiation step in the absence of oxygen. So of course, in the real system, we have oxygen, but first we start with the simplest case. Forget about the oxygen, let's write the reactions only for the fuel. So the first one is unimolecular fuel decomposition. Unimolecular means, of course, no binary collision partner. And it's a decomposition reaction which produces either an alkyl radical and an H atom or 2 alkyl radicals. And the path leading to H radicals are only important in the reverse direction because they can be like a recombination. This can also be a termination reaction, right? So the reverse of the unimolecular decomposition is a termination. So we always write that. And you see here, first thing we do is we write this reaction as H plus alkyl radical goes to form 4-methylheptane. I should write them all as reversible. Okay, in the model, they will be reversible. But for simplicity's sake, I just put the arrow in one way. So the reverse rate will come from the thermal. Now, why do I write this rate in the recombination direction? I could write it the other way around first, and prescribe the rate. Remember, I will write the reaction in this direction, and I'll write the forward rate constant. If I write the reaction in the other direction, 4-methylheptane decomposes, then I prescribe the rate for the decomposition reaction. But there's a simple trick. I don't write the reaction in the decomposition direction because it's much easier to find the rate for the recombination reaction. So because the H radical and the 4-methyl radical, 4-methylheptyl radical, are 2 radicals. 2 radicals recombining together, the rates of that are pretty well known because radical-radical reactions are very fast. They're almost pretty much at the collision limit. There's very little barrier to be overcome for this reaction to happen. So it's actually the simple, we just provide pretty much close to the collision limit. Any alkyl radical reacting with hydrogen in a termination reaction has a rate of 1 times 10 to the 13 centimeter cubed mole per second. This is the K, okay? And you see there's no temperature dependence because radicals want to come together. Yeah, they don't need any temperature dependence to come together. There's no activation energy either because again, it's a barrierless reaction. And then it makes it very easy because now if I have accurate thermal for this guy and this guy, the reverse reaction, which is the one I really care about, is going to be very accurately calculated. Because as long as the thermal is right, the reverse rate, which is the decomposition rate, will be accurate. And yeah, so many reactions, sometimes in the model we write them in one direction because we can prescribe the rate accurately for that direction. And then if we know the thermal is right, we can then get the calculation for the reverse rate very accurately. And that's the case here as well, okay? And the same thing here, unimolecular field decomposition. This other option is you break the CC bonds. These are the ones that are more probable. So because the activation energy required to breaking a CH bond is very high, but for a CC bond, we say 85 to 95 kcal per mole. It's much easier. So take a minute. How many unique CC bond scissions are there for the molecule 4-methylheptane? I want you guys to think about this. How many reactions do we have to write to cover all the different initiation reactions, the CC initiation reactions? So take a minute. Maybe you talk to your neighbor also, and let me know what you think. All right, who has a number? Anybody? Yeah, in the back? 4, okay. The first one? Between 1 and 2, okay, this bond breaks, you form a methyl and, let's say a hexoradical or a heptoradical. Yeah, the second is 2 and 3, you break that one. Yeah, and then this methyl here as well. So 4 unique scission reactions. The other side is the same. So actually the thermal takes care of that because you consider the symmetry of the molecule. So when you only write the reaction for these 4 different bonds, and of course some of them, because the for 4-methylheptane is symmetrical, it'll be accounted for in the thermodynamic data for the reverse reactions, okay? And so the first one makes methyl, it's shown here, yeah? The second one makes ethyl. The third one makes propyl. And the fourth one also makes methyl. And then we don't care about the rest. So we write 4 unique reactions in the mechanism. And then we have to prescribe rates for these reactions, okay? So where do we get the rates for these different reactions? This is a paper by Dr. Klippenstein at Argonne National Lab, and he made our life very easy. Okay, what he did is he did a lot of quantum chemistry calculations for the recombination of different radical species going together. And again, H radical recombining with something is at the collision limit. It's super fast, so we don't care about it. But other molecules like alkyl radicals recombining, they don't necessarily recombine as fast as H radical does to something else. There will be some barrier to the reaction. And he's calculated at very high levels of theory from quantum chemistry the rates of different reactions. He uses a technique called variational coordinate transition state theory, which is needed whenever you do radical-radical interactions, because we call it variational transition state theory because it's a barrierless reaction, so there's no activation energy really to calculate. So you need to follow the reaction path completely from the beginning to the end, and it requires a very high level of theory to do this. And yeah, he's one of the few experts in the world that can do this very well. So he did this in 2006, and he made these plots you see here. He calculates K as a function of temperature for different types of recombination reactions. The first recombination reaction he shows is methyl plus methyl. It's shown here in the red line, okay? Then he has ethyl plus ethyl, C2H5 plus C2H5, isopropyl plus isopropyl is shown here, and then tert-butyl plus tert-butyl is shown here. And I think he says in the caption, he's compared these to data combined from Sang and co-workers, which is the dashed line, and then his calculations, which are the solid lines. And he calls these self-recombination reactants, recombination of two self-radicals, same radicals. So previously, before Klippenstein, there was a very famous kineticist, Wing Sang. Everybody used to get rates from Wing Sang. He worked at NIST, and I think in Maryland, yeah. And Wing Sang is like the godfather of kinetics, experimental kinetics. So he has a lab in NIST, NIST, and yeah, they have shock tubes, and I'll show you later how they measure these kinds of rates. And they measure different scission reactions and try to compile databases, all based on experiments and then rules of thumb. Then, of course, people like Klippenstein come along, though, with very high accuracy quantum chemistry calculations, and they can do better than experiments. Because experiments have limitations, especially these types of experiments where you're dealing with radicals and actually measuring rates. But he shows they're pretty close. You know, they're within a factor of 2. So the dashed lines and the dotted lines are pretty close to each other. So his rates are not too far off. Again, for tert-butyl recombination, his calculations are pretty much overlapping with the experiments that Wing Sang had done. Okay, so based on this, he starts developing these types of equations. So a fitting equation, A factor and activation energy, right? And for two different radical recombinations. And he's written these down now for all different kinds that he calculated. Methyl plus methyl, methyl plus ethyl, methyl plus isopropyl, methyl and isopropyl plus isopropyl. And he said there's what we call a geometric mean rule that relates this recombination rate of two radicals based on, again, if you want to get two radicals, you take the self recombination, so two radicals AA combining together times the rate of BB together, multiplied by 2, and go to the 1/2, and it works. You get the rate for two different radicals combining together. And that's how he gets this whole list. Now, he has not done it for 4-methylheptane, but he has done it for many things that look like 4-methylheptane. So I just take, for example, he says methyl plus ethyl he's given me, but we want this one between 1 and 2, methyl plus some long chain hydrocarbon. Well, this guy only sees the adjacent carbon like an ethyl group. So the rate is going to be very similar to the same one here, methyl plus ethyl. Yeah? For the addition of this N-propyl to the breaking of this bond, so 3 and 4, you know, we kind of have an N-propyl group here, and we have a tertiary addition on this side. So he has a rate here of ethyl plus isopropyl, which pretty much is the same, the addition of a secondary to a tertiary. He's done it for small molecules, but the rate will be very similar in the large molecule because the reacting environment is the same. So these are the types of estimations we use. Right? We use his nice database, and we take it as an analogy to larger molecules. Is it exactly right? No, I mean, you could do a quantum chemistry calculation and redo it, but it'll be a very expensive calculation, and probably the estimation that we have is good enough. Okay, so I'll skip. This is for alcohols, okay? If you want elimination reactions, okay, for alkanes, it's pretty straightforward. We only have these types of unimolecular fission reactions. When you have alcohols, it's a bit more complicated. There's one other kind of reaction. We call these unimolecular elimination reactions, and that's what's shown here. So when you have an alcohol like ethanol, you have to worry about one other type of initiation reaction, because there's hydrogen here. There's 3 hydrogens here on this carbon. Well, this hydrogen is attracted to this oxygen. That's hydrogen bonding. Yeah? And whenever that can happen, so ethanol, as you heat up ethanol, it will self-dissociate to form ethylene and water, okay? And because this hydrogen starts getting connected to this guy, and they come closer and closer together, and you have an elimination reaction where the water leaves. So you break this CO bond, and you form ethylene plus water. Yeah. And that's what's shown here. So some molecules, it's okay, you gotta think, there might be new reactions. So anytime you have oxygen in the molecule or sulfur, there's other types of initiations. For alcohols, you gotta be considered what we call force-centered elimination reactions. And I mean, I wrote a lot of papers about these different alcohols, so we've developed rate rules for these as well, and you can use them. Again, depending on the structure of the alcohol, you'll have different types of products and different rates. Okay, so how could we measure the rates? You could also measure the rates for the different reactions. I showed in this case of 4-methylheptane, we could use these self-similarity rules, right? But for some molecules, again, you want to measure. So as an example, this is the measurement of all those different initiation pathways for 2-butanol. This is work, I think, done in Stanford. No, oh, sorry, this is also Wing Sang, yeah? So Claudette, she was a postdoc, but now she's a staff scientist with Wing Sang. So this shows you how they measured the rates for initiation. So for a molecule like 2-butanol, you have different types of initiation reactions. Again, losing a methyl group to form this intermediate, losing a hydrogen. You also have the elimination reactions, losing water, and another reaction to lose a methyl group. So they take 2-butanol, or any molecule, they put it inside of this shock tube, okay? And they fill up, this is what we call a single pulse shock tube, which is different than your standard shock tubes, which are used for measuring ignition delay times, because most shock tubes, they have reflections of the shock waves, which cannot be used for direct kinetic measurement. So here they use a single pulse shock tube. You basically have a shock tube with a driver gas on one side, a diaphragm, and a driven section where you fill up your reactant mixture. In this case, the reactant mixture is only 2-butanol, maybe in some inert. So because they want to do a decomposition reaction. And then they break the diaphragm. When they break the diaphragm at time 0, you have a shock wave which increases the temperature. And then, because of the increase in temperature, then you have the onset of some chemical reactions. And in their reactor, or their shock tube, they're extracting the gases from the shock tube through a sampling port and taking it to a GC. And from a gas chromatograph, then, they're tracking the product concentration as a function of temperature in the reactor. And all of this has to be done very quickly, so they have a very fast sampling port to extract the gas sample very quickly after the reaction has happened and take it to the GC and measure it. And what are they measuring? They're measuring all of these different species that are being formed. And again, they're saying that the only products that can be measured are those ones from the initial decomposition of the fuel. So they have to be sure, right? So they have to make sure when they open the sampling port, it's really frozen information in the kinetically governed region of when that decomposition happened. If they wait too long, all those products are going to interact with each other and you'll have a mess of a soup, like any combustion experiment, right? But if you open this port at the right time, right after the decomposition happens, then you can measure these species that are being formed. And they'll do this at different temperatures, and then they'll get the rate of formation of these species as a function of temperature, and they can fit a K value. And that's what they do. So they measure then, things like the different alkenes that are formed, cis-2-butene, trans-2-butene, 1-butene. They measure this decomposition of 2-butanol to these different species as a function of temperature. They measure the other aldehydes, ethylene, acetaldehyde, propene, the species that we saw here that are a product of the fission reactions, and then they fit the rates. And like this, you have papers that do this for many different fuels. They've done it for alkanes, alcohols, but they're time-consuming, studies. Yeah, I think very few groups are doing this. Brzezinski's group at UIUC in a single pulse shock tube. Wingsang's group. Then you have other groups like Stanford, KAUST. They do this with laser diagnostics. They don't need single pulse because they don't need to extract the samples. They can do it in a regular shock tube using laser diagnostics. We'll see some of those examples later on as well. So it can be done experimentally, but nobody's going to give you money to do it for 4-methylheptane. Yeah, people did it for different butanol isomers about 10 years ago under the funding from the CEFRC, which was also what funded this initial Combustion Institute summer schools, Princeton summer schools. But now people don't fund these things that much anymore. So we rely more on computations. Okay, so you can get the rates for unimolecular fuel decomposition from either experiments or theory. And both of them are nowadays giving pretty good agreements. Nowadays we rely more on theory just because experiments are becoming increasingly expensive. And again, these types of single pulse shock tube facilities, there are much fewer in the world today than there were like 20 years ago. So that's the first reaction class. What about the second one? H abstraction from the fuel. So the first is an initiation. Once you make some radicals, they'll go and abstract back from the parent fuel, right? So abstraction can happen by any radical in the system. H, OH, HO2, methyl radical, fuel radicals. In the case of 4-methylheptane, hydrogen can be abstracted from primary, secondary, tertiary sites, and the rate will depend on the type of the radical and also the type of the hydrogen that's being pulled off. So how many unique H abstractions are there? Anyone can say right away? There should be 5, right? So we have one here from the number 1 site, the number 2 site, number 3 site, number 4 site, and the last methyl group in the middle should be the 5th hydrogen abstraction. So there's only 5 hydrogen abstraction reactions for the fuel, but of course, this has to be done with many different types of radical partners. So how do we do this? We can write the reaction straightforward. H plus fuel gives us radical on the 1 site, radical on 2 site, radical on 3 site, and so on. But we need to assign rates. So we typically provide rates on what we call a per H atom basis, okay? Let's say the hydrogen is abstracted by H radical. So H radical from a primary site will abstract hydrogen at a rate of 2.2 times 10 to the 5 with N of 2.54 and 6,756 activation energy. Okay? And we prescribe this on what we call a per H atom basis. So remember on this site, there's 3 hydrogens that can be pulled off. You don't write the rate for 3 hydrogens, you write the rate for 1 hydrogen, because again, from the thermal data, you know that there's 3 hydrogens on this site, and from the structure of the molecule. Similarly here, similarly on 4 and 5. And then so for OH, for methyl, for HO2, we can have different types of rates based on the type of carbon atom that's there. So one type is primary, we say the P, 2 is a secondary, 3 is a tertiary. In this molecule, 4-methylheptane, you only have primary, secondary, tertiary. This is the simplest way to do it. You can say the first approximation to calculate these rates. And then if we want to then see how this, then if we want to ask the question, which abstractors are the most important in fuel oxidation and pyrolysis? Well, in pyrolysis, you have H, methyl. There's no oxygen around, so these are the key features, key radicals. But whenever you have oxygen around, you make OH. So OH is going to be the most important radical species that's pulling off hydrogen from your fuel. And what do the rates look like? Well, this is a rate, for example, the rate constants from OH on a per H atom basis. If you were to pull off a hydrogen from a tertiary site, you could see it's very fast. Yeah? But then as temperature increases, secondary sites start catching up. And primaries, well, primary we said has the highest bond dissociation energy, so they're the weakest hydrogens to pull off. They are the weakest. But remember, on a per carbon site basis, we have 3 hydrogens on a primary, 2 hydrogens on a secondary, and 1 hydrogen on a tertiary. So we have to multiply all these rates by 3. 3 for primary, 2 for secondary, and 1 for tertiary. So actually then you start to see all of these can be quite competitive with each other. So you should include them all in the model. Okay, that's the basic way to do it, right? We just consider primary, secondary, tertiary, primary. But again, people nowadays, we are more eloquent and elegant in determining the rate constants. So group at Argonne National Lab, Siva Ramakrishnan et al., and also, I'll show you in the next slide, a group from KAUST, they find a much better way to describe the rate. So they say the rate from, in my simple formulation, the rate of abstraction from this primary and this primary are the same, because I only have one rate rule. But they say no, the rates are actually different, and they got this from measurements. So these measurements are done in shock tubes, but not in single pulse shock tube. They can do this in a standard shock tube because it's a radical abstraction reaction. They take a molecule like tert-butyl hydroperoxide, TBHP. They fill that into the driven section, and they fill a fuel molecule. And once they initiate the shock, the TBHP breaks down to OH, and they measure the rate of the OH decay as a function of, they measure the rate of water formation, because OH is going to go and grab hydrogen from the fuel. So they measure the rate of water formation using a laser, and then they see, okay, they can measure then the rate constant with laser diagnostics. Really, really nice, elegant, very little error, because it's such a clean experiment, yeah? So OH abstraction from the fuel, they say that it depends on the neighboring environment. So they say that this is a primary carbon, this is a carbon, but this carbon is bonded to another carbon and 2 hydrogens. This carbon is bonded to a primary carbon and a secondary carbon. This carbon is bonded to a tertiary carbon. So they consider not only the nature of the carbon site, but also what is it bonded to, the neighboring environment. So they call this the next nearest neighbor. And then depending on the neighboring environment, they assign a rate constant. And they've measured this. And how do they do this? Well, they measured many different alkanes, like ethane, propane, butane, isobutane, branched hydrocarbons. They actually measure the rates. And then based on the neighboring environments, they assign different kinetic parameters. And this is the table from KAUST group, Professor Farouk and Dr. Badra. So based on the different types of primary sites, they have different rates. So actually P0 is a primary bonded to another primary. So in the molecule of ethane, this is P0. Okay? A primary bonded to another primary is given the notation P0. A primary bonded to a secondary is P1. So this is P1 because it's a primary bonded to a secondary. And then a primary bonded to a tertiary is P2. So this is P2. This carbon here is a P2 because it's a primary bonded to a tertiary. And then a primary bonded to a quaternary is P3. We don't have that here in this molecule. Similarly, S00 is a secondary bonded to two primaries. So it's the middle of propane. So if you have propane, this is S00. This one becomes S01. It's a secondary bonded to a primary, a 0 and a 1. And like this, they've got this whole table. And how do they do it? Well, they bought like a bunch of chemicals with every single combination of these things, and they measured the rate. Yeah? And, well, it's nice because they only had to do it once, and took about two years and many different experiments. And now we have all the rate rules to very high accuracy. So now, for hydrogen abstraction, we don't rely on computations because they've done the experiment, and it's pretty much done. Yeah? We have all the experiments we need for hydrocarbon fuels. Of course, now if we have oxygenates, someone has to do the experiments again. If you add other group atoms like nitrogen in there, we don't have the rules. Okay, so this is how it looks. You know, you have these rate constants. Which are the important fuel molecules? Well, H, OH, methyl, HO2O. We include them all, but you see here the rates for things like methyl abstraction and HO2 are very slow, but things like H, OH, O radical, they're very fast. So some reactions are much more important than others. Okay, so we're going to leave it there for today. Now it's 12:20. We have a career panel, I guess, for lunch at 12:45, so I'll see you guys there. Okay, and see you tomorrow.